Today, I shall discuss the Bohr's correspondence principle. Bohr's correspondence principles. Already, it is now known that the theories for microscopic particles is some sense finer than that of the macroscopic bodies. But in some situations, it is possible that some behavior of the microscopic particles resembles the classical domain. And Bohr states that the classical results and quantum results in some situations becomes identical in the context the n, the quantum number describing the system becomes very high. In that case, the quantum result and classical result merge together when n tends to infinity, means very high. And this is the correspondence principle. Means these quantum results and classical results are merging together. One corresponds to the other when the quantum number describing the system is very large, tending to infinity. I shall discuss here the three systems one after another in which I try to show the frequency of radiation absorbed by the system obtained from quantum theory and also from classical theory. Both are same, both corresponds to each other and they are merging provided the quantum number describing the system should be very high. First, I shall discuss the Bohr hydrogen atom. Bohr hydrogen atom. First, I shall discuss this Bohr hydrogen atom. Already we know in my previous lectures I have also stated that the electron is revolving in a circular path, keeping this nucleus at the center, and this is the R. This is the R. R is the radius of this orbit in which the electron is moving. So the frequency of radiation calculated by quantum theory for this hydrogen atom is that the energy of the hydrogen atom equal to 1 minus 1 by n square into 2 pi square m e to the power 4 divided by h square. We can write in short minus a by n by n square, where a equal to twice pi square m e to the power 4 divided by h square. This term within the bracket. Now I take this A. Then the energy difference between the two successive levels delta E equal to En plus 1 minus En, and this is equal to this minus A divided by N plus 1 whole square minus plus A by N square, and so this is equal to A into twice 1 by N square minus 1 by N plus 1 whole square, and this is the energy difference between the two successive levels N and N plus 1, and this equal to twice N plus 1 into A divided by N square into N plus 1 whole square. Now if we take this postulate, now if we take this condition that n tends to infinity, means very large, then twice n plus 1 we can write almost equal to twice n, and n plus 1 almost equal to n. In that case, the delta E equal to 2A divided by n cube. 1 n will be cancelled. So if we, whenever the hydrogen atom absorbs radiations of frequency nu, this can excite this hydrogen atom from this n level to n plus 1 level, and the energy one transition requires the absorption of one photon, and the energy of the photon is equal to h nu, and this h nu must be equal to the delta E, means delta E equal to twice A divided by n cube, or frequency of this radiation absorbed by the hydrogen atom for the excitation is equal to twice A divided by n cube h. H is the Planck's constant, n is the quantum number, n is high. So this is the frequency of radiations absorbed by the hydrogen atom for its excitation, and this frequency is sometimes also called the perturbation frequency. This nu sometimes called perturbation, perturbation frequency, means this frequency of radiation actually disturbs this hydrogen atom from its equilibrium position, from its stable state. So this frequency is sometimes called the perturbation frequency. If we now calculate this frequency of radiation from classical results, calculation of frequency of radiation from classical theory, then we shall find in classical theory it is stated that the frequency of rotation of this electron in hydrogen atom will be equal to the frequency of radiation absorbed. Whenever the frequency of rotation of this electron will be equal to the frequency of radiations, then this hydrogen atom will be in resonance with this radiation, and the energy exchange between the hydrogen atom means matter with this energy means radiation is exchanged. So frequency of this electron moving in this circular orbit will be equal to v. V means velocity of this electron moving in circular path, and this by the circumference of this orbit. So this is equal to v by twice pi r, the frequency of rotation of this electron in the hydrogen atom. But v equal to twice pi square divided by nh, and r equal to n square h square divided by 4 pi square m e square. These two are calculated for the hydrogen atom by using this formula, using these two formula, mvr equal to nh by 2 pi and centrifugal force equal to this centripetal force E square by R square. By using these two formula, it is possible to calculate the value of V and R. If we put V and R in this relation, in this expression, then twice pi E square by NH divided by N square H twice pi into N square H square divided by 4 pi square M E square. M E square. And the calculations will give you the twice pi E square by NH into 4 pi square M E square divided by twice pi N square H square, and this will give you twice pi we can cancel, and it is the 4 pi square M e to the power 4 divided by N cube and H cube. We can write this one 2 by N cube H, and within the bracket 2 pi square M e to the power 2 pi square M is e to the power 4 divided by H square, and this term within the bracket we have already abbreviated as A. So this will be equal to twice A divided by N cube H. Thus it is seen that this is the frequency of rotation of the hydrogen, rotation of this electron in hydrogen atom, and this must be equal to the frequency of radiation. This is called the system frequency, and system frequency becomes equal to the frequency of radiation, and in that case resonance occurs. So the frequency of radiation in these two cases, becomes identical. Means so the results in quantum mechanics corresponds to the classical results, provided the n is very high. Frequency quantum number describing the system must be very high. Now I illustrate this Bohr's correspondence principle for the rigid rotator. For this rigid rotator or free axis rigid rotator. Already I have discussed this rigid rotator, and this is M1, this is M2, and this is the axis passing through the center of gravity, passing through the center of mass, and this is rotating. While it is rotating, the angular azimuthal angle or the angle of rotation is changing from 0 to 2 pi. So in this case, energy of this nth level for the system, already we have deduced n square into h square divided by 8 pi square I. I the moment of inertia, where I equal to moment of inertia of the system, and this one equal to mu r square. R is the distance between the two centers of the bodies. So del E, energy difference of the successive level, En plus 1 minus En equal to twice n plus 1 whole square into h square divided by 8 pi square I minus n square into h square divided by 8 pi square I the moment of inertia. So this will give you twice n plus 1 into h square divided by 8 pi square I. But the condition for the Bohr's correspondence principle is that the system describing the quantum number and describing the system must be very high, means n tends to infinity, and in that case twice n plus 1 almost equal to twice n. So delta E becomes twice n, means n h square, and it is 4 pi square I, as 2 will be cancelled. So for the transition, the frequency of radiation for the transition, there will be absorptions of one photon of energy h nu. H nu is the energy of this photon, and this one equal to delta E, and this one equal to n h square divided by 8 pi square I. Thus we see that frequency of this radiation absorbed for this rigid rotator for its excitation equal to one h will be cancelled, and so it is nh divided by it is 4 divided by 4 pi square I, 4 pi square I. So this is the frequency of radiations absorbed by this rigid rotator in term by the calculations of the quantum theory. Now classical theory, if we use this classical calculation of new frequency of this radiation, then this nu equal to frequency of rotation of this rigid rotator will be equal to the angular velocity, means this angle covered by one unit time, 1 second, and divided by twice pi. Twice pi is the angle covered for one rotation. So omega by 2 pi it will give you the frequency of this rigid rotator. Now we know the energy of this rigid rotator equal to n square h square divided by 8 pi square I, and in terms of this classical way, the energy of this rotator will be equal to half mv square, and this one equal to half m omega r whole square, and this is equal to half m r square into omega square, and this is half I omega square. I is the moment of inertia. So we can equate this one and this one. We shall get this value of omega, angular velocity. Half I omega square equal to n square h square divided by 8 pi square I. So omega square equal to n square h square divided by 4 pi square I square. So omega is equal to nh divided by twice pi I. So the frequency of the rotation of this digit rotator omega by pi equal to omega, we can write nh divided by twice pi I and divided by twice pi, and this give you the frequency equal to nh divided by 4 pi square I. And according to the classical mechanics, this system frequency must be equal to the frequency of radiations for its resonance. So frequency of radiation calculated by quantum mechanics, quantum theory, and calculations of frequency calculated by classical theory, both these two are found to be same, and this is the Bohr's correspondence principle. System particle in 1D box. We shall try to illustrate the Bohr's correspondence principle in particle 1D box. It is the box, and here is the particle of mass m, and 0 to L the box length, x is changing in this fashion, and it is coming to and fro motions, and potential energy within the box equal to 0, and potential energy outside the box tends to infinity. Already we have discussed. Now the energy of this particle in one-dimensional box equal to n square into h square divided by 8 m L square, where L is the length of this box, m the mass of this particle, n is the quantum number. So delta E equal to En plus 1 minus En equal to twice n plus 1 into h square divided by 8 m L square. But condition for the Bohr's correspondence principle is that n is very high. The system describing the quantum number describing the system must be very high, tends to infinity. Then twice n plus 1 we can write almost equal to twice n. So delta E equal to 2n h square divided by 8 m L square. 2 will be cancelled, so it is n h square divided by 4 m L square. So whenever the photon is absorbed for the excitation of the state from n to n plus 1, this h nu will be equal to delta E, and this is equal to n h square divided by 8m 4m L square. Thus, frequency of this radiations absorbed equal to NH divided by 4 L square. This is the frequency of radiations absorbed by this system, particularly in one-dimensional box, for its excitation. Now we find the classical calculations. It is quantum calculations. Quantum calculation, or the calculation based on the quantum theory, and it is the classical calculation. Classical calculations. Now the frequency of this motion of this particle means the velocity along this x-axis, Vx, means the distance covered in 1 second time by this particle, and for one complete motion, it requires twice L. So twice Vx by twice L will give you the frequency of the motion of this particle in one-dimensional box. But energy equal to kinetic energy plus potential energy, but in this case potential energy equal to 0, so this is kinetic energy only, and this one equal to half mvx square. This is the kinetic energy, and this energy, according to this, we know that this one equal to n square a square divided by 8m L square. So this equating these two, we have the Vx equal to Vx square equal to n square h square divided by 4m square L square, or Vx equal to nh divided by twice m L square. So this frequency of this rotation, frequency of this motion of this particle, which we call the system frequency. This is system frequency. This is sometimes called the system frequency, and the system frequency nu equal to nh by twice m L square and divided by twice L, and this will give you the value of this nu equal to nh divided by 4 m L square. So this is the system frequency, and this system frequency becomes equal to the frequency of radiation for its absorption. Then only they will be in resonance. So calculations of this frequency of radiations absorbed by the system from quantum calculations and from classical calculations are found to be same, provided the quantum number describing the system must be very high. In that case, in that context, these two results merge together, and this is the post-correspondence principle. So with this lecture, I totally complete all the topics of this quantum theory, and again I thank you to all my viewers who are watching this video lectures. If you like, then kindly give this comment in favor of me.